Welcome back. Here we go into one of those pivotal concepts of chemistry, not just chemistry 20, but chemistry in general, stoichiometry. This is probably the main event of Chem 20, if I must be perfectly honest. And it's not as bad as you think. So I want you to consider general math. Now, if I have a burger that I'm trying to make, right? That's what we're trying to make. Fine. And I'm telling you, the way that I make a burger is we need exactly 3 pieces of lettuce. This is a recipe. It's exact. Then how many burgers can I make if I have 9 pieces of lettuce? Let's be honest, guys. This is the type of problem I could give to a grade 3 kid, and they'd be able to figure it out. If I have 9 pieces and I split it into 3, I can make 3 burgers. Oh, but it doesn't seem like that hard of a concept. Keep that in the back of your heads. This isn't as bad as you think. Let's do another scenario. What if I tell you, hey, 3 pieces of candy are given to each pair of students. So that means 3 pieces of candy for every 2 students, right? That's what we're saying here. How many pieces of candy would be required to feed 3.76 pairs? Oh, yes, I'm doing partial people. Don't worry about that. But again, think about it. 1 pair gets 3 pieces. 2 pairs gets 6 pieces. 3 pairs gets 9 pieces. 4 pairs gets 12 pieces. Well, we're not 3 or 4 pairs, we're 3.76. So this is easy math. 3.76 pairs times 3 pieces per a pair. And you can even cancel out units. Pairs cancel out. 3.76 times 3, well, we're going to have 11.28 pieces of candy. Look, guys, look what this is. This is not ridiculous math. And even though inevitably people, when they get into chemistry, that start to do the stoichiometry, go, oh, what is this? It's just ratios. It's just math. It's just figuring out relative amounts. Keep that in the back of your head as we continue. Now, when we deal with stoichiometry, or quite often shortened as stoic, we are completely fixated on something super important that we've been working on the last week and a half. Balanced chemical equations. The only way that you can properly do a prediction in the context of a reaction is if it is perfectly balanced. And this allows us to predict how much product can be created or how much of a reactant is required. Guys, this is a big deal. If you have to have a certain output, a certain amount that you produce, then the only way you're going to get that is by inputting the right amount. Let's say, for example, in the world of coronavirus, that they figured out some new pharmaceutical, some new drug, and I'm not talking hydroxychloroquine or whatever else they've come up to, where it makes a massive difference. They're like, whoa, we need to treat the area of Okotoks, Alberta, exactly 30,000 doses. And that's going to be this amount of the chemical. How much of the reactants do we need to do this? You don't want to have too little, or you're not going to have enough for everyone. You're going to have too much, or another town or city might be too low. So figuring out amounts is significant in so many different facets of society. In other words, we are looking for the correct recipe to get what we need. Alrighty, so this truly comes down to, in that balanced chemical reaction, the coefficients, right? The coefficients are telling you the relative number of moles. Now, we're not saying that every time you react something, for instance, you need exactly 2 moles of this. No, you need the proper ratio. So, for instance, if you take this one, we take nitrogen monoxide and react it with oxygen gas to produce nitrogen dioxide gas. Fine. The coefficients are the numbers in the front. So a 2 here, and so often we leave out the 1s. But there's a 1 here. So it's a 2-to-1 ratio. That means you don't need exactly 2 moles of nitrogen monoxide. That means you always have to have twice as much nitrogen monoxide as oxygen gas. And the amount is what's doubled, not necessarily the mass. Be careful, the amount. We've been focusing on amount, which means number of moles, okay? Now, visualize this. Literally, it takes 2 nitrogen monoxides to react with a single oxygen to balance-wise produce exactly 2 nitrogen dioxides. Balanced chemical equation. This is what it comes down to, guys, right? Consider how those ratios work. Let's say, for instance, I want to produce 6 nitrogen dioxides. Well, if I want to produce 6 of them, how much oxygen I'm going to have? Well, it's a 1-to-2 ratio, so I need exactly half. I'm going to need 3. How much am I going to need of the nitrogen monoxide? Well, it's a 2-to-2, so it's identical, so I'm going to need 6. Now, those are easy numbers. What if we do tougher numbers? Not too tough, but what if I want to produce 0.80 moles of nitrogen dioxide? Well, then I'm going to need half as much oxygen, 0.40 moles. And I'm going to need the same amount of nitrogen monoxide, 0.80 moles. Right? The amounts are relative is what we mean. Okay. Let's start to put this into a little bit of practice here. Here we go. Okay, first step, no exception. Always. If you don't do this first, guys, the whole stoichiometric process is honestly useless, right? You've just done a whole bunch of work for nothing. You have to balance that equation. And you have to write a proper chemical equation. So if you slacked off last week, you're going to feel it. You're going to feel it for the rest of the course. And Chem 30 is going to super suck. You need to know your reactions, guys. You need to take the time for it. I have to caution you in this COVID time. Some of you have been working so hard, and I super appreciate you. Some of you have been just copying off other people's work. And if you are trying to take Chem 30 next year and you've slacked through these last units, oh man, it's going to be hard, right? This is a key unit. You can still pick up your socks here. Start listening more to the podcasts. Be proactive in your learning, ask questions so that you are setting yourself up for your future. Okay, here we go. Here's an example for you. What if we take C3H8, which by the way is propane, and we combust it? So remember from last week, your reactions, this is a combustion reaction with oxygen. Therefore, our products are carbon dioxide gas and water vapor. Why? Because that's always the products of a complete combustion of a hydrocarbon. Okay, the mole ratio of that methane to carbon dioxide is a 1. Remember, there's a 1 here, even though we don't write it, it's there, compared to the carbon dioxide, a 3. Hence, 1-to-3 ratio. Now, what if I don't react 1 mole of methane, but I react 2? Well, ultimately, guys, that just means that whatever amount you have of the propane, we're going to just have to times it by 3, right? That's what it ultimately comes down to. That's what a 1-to-3 ratio means. Now, we're going to write it in a little bit more details because sometimes it's not that easy. So when we compare the ratio of the propane gas to the carbon dioxide gas, we see that it is a 1 mole to a 3 mole ratio. Well, therefore, we can take that ratio. We can play with it. We can say, okay, I've got a 1-to-3 ratio. What if instead of 1 mole of propane, I've got 2 moles of the propane, right? So if I've got 2 moles of that propane instead, then how many moles of the carbon dioxide am I going to get? Look what this is. This is simple cross multiplying and dividing, guys, right? It is a equation where there is one unknown. You've been doing this for years and years. It's introduced in grade 5. It's been a long time. Okay, let's go through it. Cross multiply and divide means we're going to have 3 moles times 2 moles divided by 1 mole will give us the X, right? So X moles of that CO2 gas is going to be the 3 moles times the 2 moles, right? and this is 3 moles of CO2, that's where that came from, and this is 2 moles of the C3H8, and divided by that 1 mole of the C3H8. Look what cancels out. This and this are gone. We're going to be left with moles of CO2, which is exactly what we want. Okay, end result, we're going to have exactly 6 moles of CO2 gas. There it is. Now, we did all the ratio work, but ultimately, didn't you just take the 2 moles and times it by 3? Okay, think about that. Now, technically, we also did something else. Because there's a 1 here, we actually took it and divided it by the 1 that was there, and then times it by 3. Visualize this. You can see it. Divided by the 1, divided by the 1. Times by the 3, times by the 3. Right? There's your process. If the more you think about this, the easier it's going to get. There is our divide by the 1. Why? Because of this 1. There is our times by 3. Why? Because of this 3. Okay, there's shortcuts, guys. I want you to do full processes at this point so that you get used to what's happening, but you bet there's shortcuts. Let's go through another example. In this scenario, we're still going to keep on going with our propane gas, but we're going to compare different types of things. So in this one, we're going to say, okay, calculate the moles of carbon dioxide gas if there's 1.28 moles of propane. So I'm going to go through this and kind of show you how I usually set them up. I'd say, okay, N equals, and I put it underneath the propane because that's the one that we're dealing with. N of that propane is 1.28 moles, and it's the N of carbon dioxide that's unknown, question mark, and you'll see it set up like this in your notes or similarly. How are we going to do this? Well, consider what we're comparing. We're comparing the propane gas to the carbon dioxide gas. That's the ratio we're concerned about. It is a 1 mole ratio to a 3 mole ratio. Okay, so there it is. Now, what's the part that you know already? We know the amount of propane. So that's the one I'm going to write out. Okay, it goes on top. Everything about propane is on top. 1.28 moles. And then our unknown is the carbon dioxide. In other words, this right here that I'm just outlining in yellow is the mole ratio, right? That's the mole ratio we're creating so that we can now cross multiply and divide in order to figure out the amount of carbon dioxide. So write it all out. X is going to be equal to, think about the cross multiplying. We take the 3 times the 1.28, and then in turn we divide by what's over here, which in this case is 1 mole. So equals 3 moles times 1.28 moles divided by the 1 mole. These 2 moles cancel out. We're left with an answer in moles, which is good. That's what we want. We're going to have 3 sig digs. This is kind of confusing. Let's talk about this a little bit. I have a 3 here and a 1, so shouldn't my answer have 1 sig dig? So guys, when you have a balanced chemical reaction where there's a 1 here, a 5 here, a 3 here, a 4 here, those are what we call exact values. It is exactly 1 mole of C3H8. It is exactly 5 moles of O2 gas. It is exactly 3 moles of CO2. You get the idea. And exact numbers have an infinite number of significant digits. So I could write zeros after that 5 till forever, 5.000000, blah, 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 right? It has an infinite number. So that means you are completely constrained by these sig digs in the question. Your answer, therefore, will have 3 significant digits. In other words, we will have 3.84 moles of CO2 gas. And that is our end answer for the first example. Okay, let's try another one. Ratios, ratios, ratios. Going into this one, notice right away, let's talk about those sig digs. Your answer is going to have 2 sig digs. Why? Because there's 2 in the question. We're not in pH anymore, guys. Don't get confused by what we did with pH, POH. That's an exceptional circumstance. We're back to our typical rules for significant digits. Now, in this question, we're comparing moles of water vapor to moles of oxygen gas. So in terms of what we've got, it says, okay, you've been given that there are 0.38 moles of oxygen gas, and we're trying to find the number of moles of water. So those are the two things that you're comparing. In other words, the amount of oxygen gas is compared to the amount of water vapor, okay? That is a 5 mole to 4 mole ratio. The ratios are getting a little bit more complicated, if you will. We keep going. Which one do you know? You know the oxygen, so that goes on the top. 0.38 moles. Our unknown is the amount of water. That's going to be on the bottom. There, outlined in yellow, is your mole ratio. Same process. Cross, multiply, and divide. In other words, we're going to have X equal to 4 moles times the 0.38 moles, there's the cross of the first, divided by the 5 moles. That equals X. Moles cancel out except for this one. Number crunch it all, you will get, remember 2 sig digs, 0.30 moles of water vapor. Dun, 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 dun. We're still continuing with the same formula. Same chemical equation, if you will. But let's see what we're going to compare now. Calculate the number of moles of oxygen gas. Here's your unknown. Given is the number of moles of carbon dioxide. Doesn't matter that they're weird numbers. 6.2 times 10 to the negative 3 moles. That's irrelevant. What is important is we are comparing oxygen amounts to CO2 amounts this time. In other words, it is a 5 mole to 3 mole ratio. Okay, what is your unknown this time? It's the oxygen, so X goes on the top. What is your given? The carbon dioxide, 6.2 times 10 to the negative 3 moles. Here's our mole ratio. Take it, cross multiply and divide. Let's consider what happens. We're going to have 5 moles times the 6.2 times 10 to the negative 3 moles, of course, divided by those 3 moles. Okay? X is going to be equal to, when you work all that out, 2 sig digs, guys, because that's 6.2, 1.0 times 10 to the negative 2 moles of carbon dioxide gas. Dun, da, da, da. Whoops, sorry. There we go. Look at how this goes again, to remind you. We're going from CO2 to figure out the oxygen. Okay, I want you to notice something. There's a 3 in front of the CO2. There's a 5 in front of the O2. So what I end up doing is dividing by 3, because that's where we started, and timesing by 5. See the pattern here. And look, indeed, we did divided by 3. And we did times by 5. There's little hints, little shortcuts, patterns for this. I want you for this week to be showing all your ratios, all your work, but I recognize that there is a shortcut, and we'll start to talk about utilizing that shortcut if you want to in future weeks. Not this week. Show the ratios this week, please. Okay, let's do another one. Number of moles, calculate, of C3H8. So here's our unknown. If you have been told that there are 758.3 moles of water vapor. In other words, for this one, we are comparing the propane C3H8 to the water vapor. And when we look at the mole ratio of that, it is a 1 mole to 4 mole comparison. We don't know the amount of the propane, but we do know the amount of the water vapor is 758.3 moles. La la la, a mole ratio. You get the pattern. Cross multiply and divide. We're going to have 1 mole times 758.3 moles divided by the 4 moles will give us X. And when we calculate that out, X is equal to, notice 4 sig digs, guys, okay? We will have 189.6 moles of propane gas. There it is. Mole ratios. Now, we did all of those with quite a process in the exact same balanced chemical equation to kind of show you here's how this works. And let's start to do some other examples momentarily. But first, check out those ratios again, right? We're starting at a water with 4 moles, and we're ending at propane with 1 mole. So how did we go through it? Well, we divided by 4 and we times by 1. And once again, check that out. We divided by 4 and we times by 1. Patterns. Okay, here's another example from your notes. What amount of zinc? Ooh, I don't give you the actual balanced equation here. You gotta build it, guys. Is produced by, here's your type of reaction, decomposition. And you've been given an amount as well, 0.40 moles. What's decomposing? It is zinc phosphate. Whoo, lots going on. So we are going to be comparing zinc to zinc phosphate. But first we need a balanced chemical equation so we can do that. Zinc phosphate. Zinc is a 2+ ion. Phosphate is a PO4 3- ion. So let's start with it because it's decomposing. We're going to have to drop and swap, so there will be 3 zincs to every 2 phosphates. In a decomposition reaction, the ionic compound starts as a solid. There's no water involved here. And it's going to split into its individual ions, or elements, sorry. Guys, there's issues with this. It is not decomposing into zinc and phosphate. Phosphate is not an element. No, it is decomposing into zinc solid. It is decomposing into phosphorus solid, but phosphorus is weird. It's P4 solid. And it is decomposing into oxygen gas, right? They are individual elements. Let's balance this thing now. When you start to look at it, the phosphorus creates an issue. There's 4 phosphorus on the right. There's only 2 reacting, so I need to put a 2 here right away. Now I'll have 2 times 2, 4 phosphorus. I also have 2 times 3, which is 6 zinc. And my oxygens, I've got 2 times 4 is 8, times another 2. We need 16 of them. I'm not going to write 16 here. No, because there's a 2. I need to write 8. 8 times 2 is 16. This is now balanced. Consider those coefficients. 2, 6, 1, 8. Okay? What are we comparing? We're comparing the zinc to the zinc phosphate. So the zinc phosphate is compared to the zinc solid. What is the mole ratio of those two? It is 2 moles compared to 6 moles. Which is our given amount? Well, look at the question. It says N is equal to, you are given 0.40 moles of zinc phosphate. The question says what amount of zinc will result? There's our givens. So I know the amount of zinc phosphate. I'm going to write that above, 0.40 moles. It is the zinc solid that is my unknown, my X. Once again, here's your mole ratio. Okay, keep going. 6 moles times 0.40 moles divided by 2 moles. This will give us X. Moles cancel out. We're left with moles. 6 times 0.4 divided by, where are we here? 2. And we end up with a grand total of, oops, I'm in the wrong thing. Here we go. Equals 1.2, 2 sig digs because of that 0.40 of zinc solid. There it is, guys. All doable. Okay? Let's do another example. Last one. So step 1 always has to be create a balanced reaction. Okay? Then get your mole ratio. In this situation, what are we doing? We are forming benzoic acid. Now, benzoic acid does not have the hydro in front. It is simply an anion with hydrogen. Which anion is it? Well, oic, this ic comes out of 8 enzymes, so that means this must be benzoate. Benzoate is C6H5COO negative. What's it going to combine with? It's going to combine with hydrogen to form that benzoic acid. So if we're forming that arrow, we are forming C6H5COO. Put the hydrogen on H. Now you guys wouldn't know this, so I wouldn't, if you left it blank, you'd be fine. This is actually solid. I know acids are normally aqueous, but there's no water present here. We're forming this organic acid. Okay, so what comes together to form it? Not benzoate and hydrogen, individual elements. Carbon comes together to form it. Plus hydrogen gas, H2, be careful, comes together to form it. Plus oxygen gas comes together to form it. Pay attention, be careful. How much of everything? Well, I've got 6 plus 1 carbon, so I need a 7 here. How many hydrogens? I've got 5 plus 1, so I need 6 in total, so put a 3 here. How many oxygens? 2. Oh, and I'm already reacting 2. There we go. In terms of our ratios, we've got a 7, a 3, a 1, and a 1. Those are our coefficients, and in this particular question, it says what amount of hydrogen is consumed, so hydrogen is our unknown, and exactly 0.366 moles of carbon react. Those are the two things we're comparing, carbon to hydrogen. Keep going. Carbon solid compared to hydrogen gas. Look at the numbers in the front. It is 7 moles of carbon to every 3 moles of hydrogen. You've been given to use with that ratio that there are 0.366 moles of carbon. Find out the amount of hydrogen required to react with it. There is the ratio we use. Cross multiply, divide, same. We're going to have 3 moles times 0.366 moles divided by the 7 moles. Sorry, my writing's messy down here. It's so little. Moles cancel out. X is equal to, we need 3 sig digs, guys, because of the 0.366 in the question, 0.157 moles of H2 gas. And there it is, the very beginnings of stoichiometry at its most simplistic. The hardest thing about this week is making sure your reactions are correct, and not just correctly predicted with reactants and products, but correctly balanced. If you mess up the balancing, the stoichiometry is now wrong. Guys, this is simplest, right? We are going to build on this next week. So step by step, double check your work, make sure it's correct. You're now able to finish the rest of the assignment. Number 9 actually has 6 parts to it, A, B, C, D, E, F. Make sure you do them all, please, in relation to stoichiometry. And I hope that you guys did have a wonderful Monday off. And right last week on May 18th, we've had our nice long weekend. It's done. But we are quickly approaching the wonderful world of summer. So stay strong, keep going. Let me know you got questions. Take care all.